Math 265A, Cuesta College. I'm Joe Vasta, and we are covering section 2.6, Continuity. So we're going to start off this lecture with a definition. So we've been doing limits, and now we're changing one section of continuity before we get into the important derivative. So, definition. A function f is continuous at a number a if and only if the limit of f as x approaches a equals f of a. So here's a checklist for continuity, and this checklist sort of covers this definition, but it kind of gives us a list to run through when they ask us if things are continuous at a number. So to see if f is continuous at a, three things have to happen. F of a exists. The limit of f as x approaches a exists. So they're basically saying that exists, that exists. Condition 3, the limit of f as x approaches a equals f of a, which is pretty much this statement. So let's go ahead and do a problem. These are the kinds of problems you'll see in your homework when they talk about continuity. So they're asking, determine the points of discontinuity. Which condition is violated? And when they say which condition is violated, they mean of these three conditions. You find the first one that's violated, and then you just stop and say, oh, item number 2 is violated, and if item number 1 worked. So our points of discontinuity. Okay, basically, your points of discontinuity are going to be points where when drawing this graph with a pencil or a pen, you have to lift your pen off the paper to continue. Okay, so you would have to lift it off there at the x value of -3, and then one would be the next point you would have to lift your pen off the paper at x equals -2, and then at x equals -1, you'd have to lift it off the paper. Even if that point wasn't up there, you still have to lift it up and go on the other side of -1. This -1 should be right below those two things. Now looking at it, it doesn't look... Let me go ahead and fix it. So it should be like right here. There. So you're like, that's cheating. No, I just drew it wrong. Okay. And so I would have to lift my pen at -3, -2, -1, and then also at x equals 1. So it looks like there are 4 times that I would have to lift the pen off the paper to continue. So let's go ahead and take these one at a time. The first place as I was running along would be x equals -3. So determine the points of discontinuity. The first one is -3. So I'll put a box around that. Which condition or conditions are violated? Well, I gotta say, so we're looking back at this again, and I'd have to say, let's move this right here, that f of -3 doesn't even exist. So the first condition says f of a exists. So I would say the condition that is violated is item 1, which is that one right there. I'll put a box around there. And we'll see if, oh yeah, that definitely fits in the picture. I was thinking it wouldn't. Okay, the next point of discontinuity, and we're talking x values. Okay, and they call them, a, find the points of discontinuity, and that, what do? They sometimes call those points a, see right here. So the next point of discontinuity is -2. So does f of -2 exist? Oh yeah, it does. F of negative 2 is the y value of that point right there. So item 1 is good. Item 2. Does the limit of f as x approaches negative 2, does that exist? Well, let's see. If you've got the two bugs walking, the guy from the left and the guy from the right are not going to meet right before they step on the x value of negative 2. So the limit does not exist. So it is item 2 that is violated. Okay, my next discontinuity is at negative 1. And it looks like there's a hole in the graph, and then right above it is a point. So negative 1 is the next point of discontinuity. Does the graph exist at negative 1? Does f of negative 1 exist? Yeah. It's this y value, whatever this is up here. Does the limit exist at negative 1? Will the two bugs meet? Yes, they will. So I guess let's look at this. Does the limit, which is probably whatever this point is, this y value right here, does the limit equal f of negative 1? F of negative 1 is this value up here. No, it doesn't. So it is item 3 that is violated. Okay, once again, because at negative 1, f of negative 1 is this point right here. It's this y value. The limit at negative 1 it's going to exist. It's going to be this y value here. So those y values are not the same. That's item 3 says they have to be the same. That's why we put item 3. The next point of discontinuity is negative 1. It's not negative 1. What am I saying? It is positive 1. Okay. There it is. It's positive 1. And let's take a look at the items. Does f of 1 exist? Well, there's a hole there, there's a hole there. You look up and down, you don't see a point. F of 1 does not exist. So the condition that's violated is item 1. So that's what they're going to have you do in the homework. Let's take a look at the kinds of discontinuities there are. And I think I should state this even though it's not in the homework or on the test, because it may be stated in a higher math class. There are 3 kinds of discontinuities. The discontinuity at negative 3 is called an infinite discontinuity. Such a long word. Okay, because there is a vertical asymptote there. The discontinuity at x equals negative 2, see, if you're trying to draw this with your pen, you have to jump up here. That's called a jump discontinuity. Okay. The discontinuity at x equals negative 1, well, really, to get to the other point on this, there's just a hole there, and so this one is called removable. So removable when there's a hole in the graph, a removable discontinuity. Okay, so this discontinuity at x equals 1 is a jump discontinuity. So let me just put jump there. I don't want to write out discontinuity again, and so that's what it is. So 3 kinds of discontinuity. Another thing to consider that other books might say is, this is just for your information, this discontinuity at negative 2, they might say that it's continuous from the left because you can get to it and fill it in. So they might say that this is left continuous at negative 2 but not right continuous. I decided not to have that be part of the official lecture just because then it gets a little more confusing. but sometimes some books will refer to things as left continuous and right continuous. We don't want to do that here. What we want to do also is take a look at this Venn diagram here. This Venn diagram looks like that. I don't know how to do this. I guess we'll just do this here. So let's just take a look at and put some things in here. It says f of a exists, the limit at a exists, and then the limit equals f of a. So the first one, the limit didn't exist and f of a didn't exist. So the first, this -3, is a discontinuity. It's right here. You don't really need to copy down this Venn diagram or do anything like that, but it's outside those three circles actually. The next one, where it was a jump discontinuity, which happened to be right here, f of a did exist, but the limit didn't exist at -2. So -2 belongs here. Now some of you are going to like this and some of you, this is going to drive you crazy. So if it drives you crazy, just skip ahead to the next part on the video. When we had f of -1 existing and the limit at -1 existing, you actually had this discontinuity being right here. Okay. Now inside here would be all the points where the graph is continuous. Okay, but the discontinuities are outside that middle circle. And then I think 1, it didn't even exist and the limit didn't exist. So 1 can go out here. It's outside everything. If this doesn't make sense, don't stress out about it that much. But I'll include that in the PDFs. Okay, one other thing that we want to do with this, and I'll put the example right here. They'll ask you to state the intervals, of continuity. Okay, each interval you can trace without lifting the pencil off the paper. So stating the intervals of continuity, the first interval of continuity would be from, well, what x value? Well, you're going that way. It's running along a horizontal asymptote, so it's coming up here. So it comes from -infinity to the x value of -3. So there's an interval of continuity. Okay, we'll just list them off. The next interval of continuity goes from -3, from that vertical asymptote, all the way up to the x value of -2. And it actually includes -2, so I'm going to go ahead and put a bracket there. So this is what you can draw without lifting the pencil from the paper. The next interval of continuity, these are x values we're talking about, would be from -2 to -1, not including those. Okay, we can't include -1 because we'd have to lift the pencil up to draw that. The next interval of continuity would be from -1 to 1, not including any of those. And the last interval of continuity would go from 1 to infinity. So when they say state or list the intervals of continuity, there they are. Those are the intervals that you can trace without lifting the pencil off the paper. Okay, let's go ahead and do another problem, and they're going to ask the same thing. Is this continuous? Well, it will be a little bit different, but it's all about continuity. Okay, so we have a piecewise defined function or a branch function, And they have 4 questions here. Is f continuous at A? And why? Okay. So let's take a look at A equals 0. Well, you don't see 0 in any of these conditions over here. But what's happening when you put 0 in? Let's just feed this guy a 0. If you feed him a 0, 0 is less than 2, and you put it over here, it's 1 over 0. That's undefined. So is f continuous at 0? The answer is no. Now they say, why? Why is it discontinuous? Well, it's discontinuous because it's not even defined. Remember these 3 conditions. F of A has to exist. So make sure that it barely fits there. Let's move this down. F of A has to exist, and then this one says, well, f of 0, if you go to plug it in here, it does not exist. So you could even say that item 1 fails. That is a word you usually don't want to write on an exam, fails, because you feel like you might be jinxing yourself. But item 1 does fail. The function does not even exist at 0. So maybe that should be the first thing we do with each of these, to see if we can see if the function exists. Okay, A equals 2. Well, if we fed this a 2, it wouldn't take the top road because 2 is not less than itself. But 2 is equal to 2, so it would take this middle road. So f of 2 does exist, so the first condition on the checklist works. Does the limit exist? Well, remember we did this in the last section. We have to see what happens when you plug 2 in here, and when you plug in 2 right there, you end up getting 2 minus 1, which is 1. But if you plug 2 right here, which we have to investigate, because we have to investigate to the left and to the right, you end up getting 1/2. So 2 plugged into this one gives me 1, and 2 plugged in here gives me 1/2. So you are going to be jumping from 1/2 to 1. So the limit does not exist. So is f continuous at 2? The answer is no. It's because the limit of f as x approaches 2, and we covered doing this in the last section, this does not exist, or it could have been a few sections ago. So this would mean that item 2 fails. Okay, let's continue. Is f continuous at 4? Now 4 is going to be another one of those boundary points where we switch from this one to this one. And so, first of all, does f of 4 exist? F of 4 is, we have to actually go on this one, it is 3. So f of 4 exists. What's the limit? So f of 4 is 3. The limit as x approaches 4. Now maybe that's going to be DNE as well. I don't know why I'm writing it out for this one. So we have to look right here. We already know that 3 is the output there, and if I put 4 in here, even though I'm not supposed to, I'm just checking what happens on the left side. I get 4 minus 1, which is 3. So I get left hand limit and right hand limit both equal 3. So the limit actually exists, and it equals 3. So does f of 4 equal the limit as x approaches 4? So we're looking at condition 3. So condition 1 and 2, good. And condition 3, yes, they're both 3. So the answer here is yes. You know, if they say why, you can say, oh, because f of 4 equals the limit of f as x approaches 4. Okay, it actually goes back to the very definition of continuous at a number. Okay, is f continuous at 6? Okay, so first of all, what is f of 6? So I should have been writing more of this down for problems 1 and 2, but I'll write it down here. So f of 6 is, well, there's only, if you put 6 in here, it has to take the bottom row. It is 1. And the limit as x approaches 6 on your function, well, on both sides of 6, you happen to be right here at 3. Because, like if you are at 5 or 7, you're taking this road right here. So the limit as x approaches 6 is 3. So item 2 is good. The limit exists. Item 3, on the other hand, that's the one that's going to fail, because the f of 6 does not equal the limit of f as x approaches 6. So this is going to be no. F is not continuous at 6, and it's because f of 6 does not equal the limit as x approaches 6. What that would look like on the graph, or on a graph, would be a hole in the graph at 6, and then like right, would it be? Yeah, it would be below the hole would be a point. Okay, at 6, 1. So this is item 3 fails. So we're analyzing this just by looking at the algebra. We did not draw a picture. If we had drawn a picture, we would have been able to figure these things out from the picture. But there are some times where you want to actually know how to look at the algebra and figure some of these things out. So there was only one of these 4 x values where f was continuous at. Okay, so that takes care of this problem. I'm just doing problems that are similar to your homework problems. Now we're going to go ahead and determine the intervals where f is continuous. So that's what we're going to do now, or state the intervals of continuity. Okay, so what do we see here? 3x squared minus x plus 1. This right here is a parabola. And this parabola opens up, and it looks like this. And you're like probably thinking, well, Joe, where's the x and y axis? I don't need it to answer this question, because with a parabola, it keeps getting wider and wider. Do you see any infinite discontinuities, jump discontinuities, or removable ones? No, it's a nice smooth graph. In fact, you can graph the whole parabola without lifting the pencil off the paper. So for the interval, or intervals where f is continuous on this one, it would be everywhere from negative infinity, these are x values, to infinity. In fact, a parabola is a special kind of something called a polynomial. And let me just write something down here, because this will be very useful. Polynomials are continuous everywhere. Okay, you can graph any polynomial from negative infinity to infinity without lifting the pencil from the paper. Okay, this right here is not a polynomial. It's a polynomial over a polynomial, which is sometimes called a rational function. determine the intervals where f is continuous. So now this is the next problem. So how can I do this problem? What I can do is find the trouble points on this rational expression by factoring the bottom. So this is x minus 1 all over, let's see if we can factor this. Here's x, and then I have a 2 and a 1, and the minus goes on the 2, the plus goes on the 1. Okay, so where are your trouble points? Your trouble points happen to be at the x values of 2 and negative 1. And in fact, at 2 and negative 1, that's where you will have vertical asymptotes. Now, if this thing had factored into x minus 1, x plus 2, you would cancel the x minus 1s, but x equals 1 would still give you a hole, and that would be a place of discontinuity. So the bottom line is, this rational function is continuous everywhere except these trouble points of 2 and negative 1. So 2 and negative 1 are bad points. So how are we going to do that in interval notation? We're going to go like this. From negative infinity to negative 1, determine the intervals. So we're just determining the intervals, we're just listing them out. We're not going to put the union. And then we're going to go from negative 1 to 2, and then from 2 to infinity. So these are the intervals where this function f is continuous. So let's go ahead and write something about rational functions. Rational functions are continuous. And we're not going to say everywhere, because obviously that's not the case, but they are continuous in their domains. So basically, if you get one in your homework and it's a rational function, all you have to do is find the domain, put that down, and then those are the intervals where f is continuous. With any polynomial in your homework, if they ask for the intervals of continuity, you're always just going to say negative infinity to infinity. So that's basically really what we have to do in our homework. Okay, let's cover something that we're supposed to cover in a calculus class. It's called the intermediate value theorem, and I have it written out here. Sometimes my lectures will go less than the allotted time. So some of you may have been thinking, I'm getting gypped off. He's not going 90 minutes every time, because I think this class meets 3 days a week or something like that. Well, one thing is, when I'm in class and I'm doing face-to-face, lots of times I will write this on the board, and that will take a lot of time. You may have noticed I have lots of things already written, because I felt like when you watched the video and I was just writing things out and mumbling as I was writing, that would be super boring. And these videos are already boring enough. Okay, so this is all written out for us. Let's go ahead and go through it. This guy right here is f. F is continuous on a closed interval from a to b, and it looks like this. Why do we know this? Because I could probably trace this without lifting my pen. Because this is the if part. F of a does not equal f of b. Well, those are y values. Those are altitudes of the graph. F of a is right here. Its y value is right there. And f of b is up there. They are not equal. Do you see? They're different numbers on the y-axis. So condition 2 is satisfied with my picture. N, they just call it n, it's a number between f of a and f of b. So we just put it on the y number line and we put it in between them somewhere. So here's what the intermediate value theorem says. So if you've got a continuous graph where this is happening, there exists a number c between a and b such that f of c equals n. So what does that mean? If you've got this set up, and I'll do this in red pen, this is the then part. There is a number on here. I want to make it perfect here so I don't mess this up. So there's a number. There's a point on that continuous graph that corresponds to the n, and it shoots down here, and so we call this C. So it says there is a number within the interval A to B such that you go f of C it equals n. And that's what the intermediate value theorem is saying. It's saying that you've got to have a continuous function to do this. You have f of A and f of B. That's what it says. And it seems very technical, but what I'm going to do is I'm going to try to connect this to our bug on a number line. Suppose a bug is moving on a number line at time t seconds. His position is s, feet from the origin. Let f of t equal s be continuous. So that's the key part. So we're going to give you a few things. The time at 1, the bug is at 10. And when the time is 5 seconds, the bug is at 4 feet on the number line. Multiple choice. There is a time in 1 to 5 where the bug is at what feet? So let's take a look at maybe a picture of the bug here. We have, that's not S. Let me just, wait, I have white out here. I can take care of that. We have time. Oh, look at this. And then we have position. That looks really bad. Oh, look, I got it on my finger. Okay. So let's see. At 1 second, the bug is at 10. And at 5 seconds, the bug is at 4. So let's put the point 110 in and 5, 4. Now the key to this is we're trying to do the intermediate value theorem where it says f is continuous and f of A does not equal f of B. So I guess we can call this A and this B, and f of A does not equal f of B. And it's continuous. So the intermediate value theorem says there's an n between f of A and B, so we'll get back to that. There exists a number C and AB. So it says there is a time in 1 to 5. So that's the then part of the intermediate value theorem. There is a number, a time. See, they didn't tell you what that time was, where the bug is at blank feet. So if you look at the intermediate value theorem, they're trying to get you to figure out what capital N is on this one. So let's think about it. Our function is continuous. It goes like this. It could go all the way up and do a maximum there and do a minimum here, but I'm just going to make it go like this. Continuous means I can draw it from 1 to 5 without lifting the pen from the paper. Okay. There is a time within 1 to 5 seconds where the bug is at. So the intermediate value theorem is going to guarantee this. At 0, at 3, at 8, or at 11. Well, with the intermediate value theorem, we're trying to find the n, because these are on the s-axis. Because it says feet. So we're trying to find the n. They didn't give us the n, but what does it say about n? N has to be between f of A and f of B. And in this case, n has to be between which two values? F of A, which is 10, and f of B, which is 4. So it has to be between these two values. So which one of these guys is between 10 and 4? Well, that would be 8. So the intermediate value theorem, it is a little theoretical, and it has to do with continuous functions. There are applications of it, but we're going to move on. Our next section, we are going to make a connection between difference quotient, our bug handouts we've been doing, and limits, and come up with something called the derivative.